Welcome back. Now I want to look at scalar line integrals and do an example both in the Cartesian form where we go through and parameterize the whole thing around and using some symmetry to rewrite it in a polar form. So a quick reminder about what a scalar line integral is. It's just an integral over a curve in space of a surface. So we have this function of possibly x, y, and z. We're moving along a path in 3 or 2 dimensions, and we want to find out what's the area under that curve, under the surface restricted to the part just above the curve. You can imagine like a wavy curtain, I think I mentioned here. It's kind of fun. So what we're going to do in general is parameterize, find a way to write how x, y, and z are tied together, and then restrict the surface. So first step is to parameterize, like I said here, either by tying the x, y, and z to some common t, or by using symmetry arguments, like talking about how the path is on a circle or on a straight line or something like that. Describing it in terms of shapes can also be used. Then second is to restrict the integrand function, which is the surface or hypersurface in this case if it's a function of z, to an evaluation of some function along the line. So you can think of this as becoming f of t, essentially. So you're going to turn that surface into a function of a single variable, t. Then we're going to scale the differential using the speed. And this goes back to the chapter on functions or vector valued functions, where we met the arc length s. And it's rather complicated in its integral form, but if you look at the derivative or change in arc length over time, that is identically equal to the speed, the magnitude of the velocity vector. So we can swap out the ds differential for the speed times dt. So we can work with a simpler time scale, essentially, by scaling by our speed. This is the stand-in for the Jacobian, the cost that we paid in 2 and 3 double and triple integrals over an area over a solid. Now it's just the speed, so allowing us to scale back how we integrate along a curve. So for this example, I want to cook an egg. And to avoid overcooking the yolk, I like to fry my egg just off the center of the pan, which is heated according to a function 200 minus half of x squared minus half of y squared. Basically, I'm saying that I'm heating this up over a gas range where its heat is greatest in the center and it radially decreases out as we move outward along the pan. So this is a surface, a heat surface, and we want to restrict, well, we want to think about how that heat plays on the egg that's just off center. So my question is, what is the size of an egg according to its radius, if we think of it like as a circular shape cooked on that pan? What is the size of egg I can cook to have an average temperature, not in the egg, but along the egg's perimeter of 175 degrees Celsius? So just for reference, 175, I think, is around 350 degrees Fahrenheit, and 200 is around 400 degrees Fahrenheit, so pretty hot. This is pan frying temperatures. So we want to measure the temperature along the egg shape, basically a circle. Let's draw this a little bit. Make some space. So here's my pan. And now I want to draw my egg. It's going to be just off center. And move that. And then add in some axes so we can see how this lines up. Okay, so there we go. There's my egg cooked just off center in my frying pan. The pan is hottest in the center, it radiates outward, or I should say the heat decreases radially. And then I want to integrate along this blue curve. So that is my curve C. Okay, so if I parameterize in Cartesian, I think of this point as being B. That point is being 2B. I have a circle of radius B. For my egg, I want to find out how big of an egg I need to get this average value. And so then I can parameterize my curve in terms of this equation, x minus b quantity squared plus y squared equals b squared. So I want to think of it kind of like a circle. So that's my x minus b will represent cosine. So I shift that back. My x will be b cosine of t plus b to cancel out there. So that represents my x of t so that I can get a nice squared term there. And then my y is b sine of t, and I can factor a b out to get my position vector. Now you may notice that there's a lot of sines and cosines moving around. This is very close to polar, but it's a little bit tricky because it's not centered around the origin. So we're going to keep going as if t is just a parameter, even though we know it's theta, right? It's going around, changing in terms of the angle. So we're going to plug in these position values for x and for y, and then look at how our surface is restricted and how much the path is changing as I move around. What is the speed at which I'm moving with this parameterization? Okay, I think I'm gonna have to delete that lovely picture. So we'll clear off for now. Okay. So first, plugging in the x and y into my heat function, I can group out the minus 1/2 b squared terms. So right there, I factored that minus 1/2 of b squared. And I can combine cosine squared plus sine squared to give me a 1 here. I have a 1 there. And together we get 2. And then I have a 2 cosine of t in the middle. If I scroll to the far end, can I simplify that a little bit? Yes. I can just highlight this final piece. There you go. The half cancels there, leaving me with a b squared term and then a b squared cosine of t, both subtracted from 200. So basically, as I move around in t, I have a certain temperature that I'm centered around 200 minus b squared. So I'm kind of feeling an average just by that, right? I'm moving around in a circle, and this cosine goes from +1 to -1, and so it alternates between subtracting from and adding to this amount. And so I'm kind of feeling like an average value already. But let me keep going. I want to then scale by the speed. So that speed ends up just being b. I take my derivative. This goes back up to my r of t function. I factor that b out and take a derivative. I get a negative sign and a cosine. Now that squares, the sum of the squares of those two values equal 1, just like cosine and sine do, it's just in different spots and negate it. And so we get a b that pops out as our speed. And now I can integrate over the interval from 0 to 2 pi. So quick check. I have my 3 pieces. My r of t, that defines my interval. So I'm going from 0 to 2 pi. Then it implicitly defines my speed, which I calculated here, b times dt. So that shows up over here. And then in the middle is what I simplified down, the 200 minus b squared cosine of t. Okay, so that's what I'm integrating. I can factor a b out, and then I look to see what I'm integrating. I have a 200 minus b squared. That's a constant, so I can factor that out. And then it's multiplied by 2 pi. And then I want to subtract out the integral of the b squared cosine of t. So I can integrate that. Cosine goes back to sine, but oh, hold on a second. Wait a second. I'm integrating cosine of t, and I'm integrating from 0 to 2 pi. Cosine of t has a period of 2 pi. And we know that the average value of sine and cosine is 0, which means that if you integrate over their period, you get 0. So basically, this whole term goes away. I'll highlight that. Let me see, can I go? Let's try color. Yes. Brown. How about red? There we go. Boom. It's gone. So by symmetry, no, not by symmetry. By properties of periodic functions, we integrate the cosine to 0. And then finally, we found the line integral. Now we want to find the average function value and compare that to 175. So we use the formula. The line integral divided by L, the perimeter length, is going to be equal to 175. Now the perimeter length of a circle of radius b is 2 pi b. And so we take our line integral value, divide by that, and notice how the 2 pi cancels out, the b cancels out, and we get our 200 minus b squared. That temperature that we noticed at the beginning right here, it seemed to be oscillating around this temperature, which gives us the average temperature around the perimeter of that egg. And so we then take 200 minus b squared equal to 175, solve for b squared, 25, solve for b, 5 centimeters in this case. So 5 centimeter egg is 5 centimeters is the radius of the circular egg which would cook to these specifications. Now you think, does that mean I can only cook certain sizes of eggs? Well, not necessarily. If you're skilled at frying eggs carefully, you could always pour it out slowly onto a hot pan, and that makes the edges rigid enough that you can have a thicker egg and keep it to a certain size. So if you want to go for a perfect egg, whether or not you want to meet these specifications or not, yeah, have fun with that. You're welcome to do your own line integral investigations. Now, before we end this example, I wanted to dig into the polar symmetry, because it felt like we were doing everything in terms of theta, but we were calling everything t. Like, why couldn't we use theta? Well, if I go to the same problem and let me try making some space here. Let's try drawing that again. I started out with my pan. Oh, it's in blue this time. Interesting. Start out with my pan, and I want to cook an egg that's just off center. But instead of drawing the axes through the center of the pan, I'm now going to draw the axes through the center of my egg. And if you want, you can imagine the axis going to the center of the pan right next to it. So really just taking that axis and shifting it over a little bit. And these new axes, well, they have new variables. We basically need a change of variables. So we call this axis U and that axis V. And V didn't change. Still the y direction. V direction is still y direction. But U shifted over a little bit. And so we need to take X and shift it by B. If we subtract B from X, we shift it to the right. So that's where we shift that the V axis. And so now we can describe our path C in terms of polar coordinates. So that simplifies how we integrate around it in terms of how we reference it and use polar symmetry, but it unfortunately will complicate the heat function. But it's the same complication we ran into when we applied our parameterization to it, so it's really not that different. I want to show you how you can jump into the problem like this, focus on getting the integration movement to be in your polar or other symmetry form, and then manipulate whatever function you're integrating to make it work. Okay, so there's our goal. Notice that this shift doesn't really change the variables much, and because there's no scaling of x and y, the Jacobian is 1, which means The cointerminant is 1, which means you don't have to really do any change between the volume, or sorry, area calculated in one space versus the other. You're just shifting the coordinates over. It's beautiful. However, I will call one u and one v. You could easily go back and just call this x, shift it over, a new x, and that is a new y. It's really not that big of a deal, but to keep things in line, to be more careful, and to line up with section 16.7, which we just covered, it is a new coordinate system. So let's clear those annotations and move on. Diving into that heat function, I plug in u plus b. Looks very similar to what we had before, except for now it has a u instead of the cosine function. We end up with a u squared plus v squared, but we know that it is equal to b squared. We're on this circle of radius b. And so that combines the b squared. We already have a b squared over here, and then we have a 2bu in the middle. So writing down what u is equal to in our polar coordinate, it's the x, right? It's the new x. So that's b cosine of theta, because it's a radius of b. And here we go. Very similar form, almost identical to what we had before. And then simplified down to a 200 minus b squared with an oscillating term around it. So again, we're predicting that 200 minus b squared is our average value. And that's exactly what we get. Let's see how it works out. Well, plugging it in, it's the same function, right? It's the same function after simplifying it. But how do we get this b d theta a little bit quicker? Well, if we swing it back up, notice that we never parameterized in terms of a position vector r of t. We just said we're traveling around a circle, radius b, using an x and a y, a new x and a new y term for theta going from 0 to 2 pi. And because of that, the arc length of a circle is r d theta, or I should say the change in arc length. The regular arc length s would be r times theta, but since we're looking over a small piece of arc length ds, that's r, the radial distance outward, times a small piece of theta. And because r is equal to b on our particular circle, that's b d theta. So moving into polar doesn't necessarily simplify the steps we need to do in the function, but it simplifies greatly how we get to the arc length, how we get to translating or scaling that differential. The rest of the integration is identical. Our cosine of theta integrates to 0 from 0 to 2 pi. It's period. The constant is factored out times the constant b times the 2 pi, the interval we're integrating over. And then we compare it to 175. We get b squared is 25, b equals 5. Again, the same values, right? Nothing has changed. It's the same answer. And eventually it turns into the same kind of problem. It's just that the polar symmetry we utilized, thinking of it geometrically as traveling on a circle with a certain radius over a certain angle, allows us to picture that arc length ds in terms of r d theta. So I hope this is helpful in visualizing how polar symmetry can allow us to get through some of this more, shall we say, complicated parameterization. And if we can avoid some of these steps, it's helpful. And I think not just avoiding work, like we're not just about avoiding work. It is so much more intuitive to think about moving around a circular path than to say you have to define some function of x of t and y of t and z of t. What is the function? Describe it geometrically. Is it a line? Is it a circle? Is it a parabola? Once you define it geometrically, then it makes more sense to describe the components and describe the differential pieces as we move along it. Okay. That's it for our scalar line integrals. We'll later look at some vector fields and line integrals with them.